So I have one more demo to introduce. This last demonstration is called Parknet. And Parknet is a joint effort out of Rutgers, WINLAB, NICTA, and NYU Poly in Brooklyn. Marco Gruteser is going to give the presentation, and he is going to tell us a surprising fact, which is that it is difficult to park a car in Brooklyn. He's also going to tell us what he's doing about it. Marco?
Thank you, Mark. It took us several years to dig up that fact that it is, in fact, so hard to park in Brooklyn as a main result of our research. Today, I'm here together with my colleagues from NICTA and NYU Poly, show you how Genie is not just useful for deep network layer experiments, but how it can also support wireless application experiments and research. In particular, we've been using the WIMAX infrastructure at NYU Poly that is also emerging at many other campus sites across the nation to conduct experiments related to a parking application that we're developing. Now, why parking? I'm sure you've all had that experience of getting to the destination, but then driving around endlessly to find a curbside parking spot. That's not only frustrating for us personally, it also incurs a large societal cost. Overall, the cost of traffic congestion in the United States has been estimated at $78 billion. And so that's based on the time, productivity lost, gasoline wasted, and several other factors. And the parking contributes a surprisingly large fraction of that. Traffic counts in Brooklyn, for example, have shown that at some times, in certain areas, up to 45% of the vehicles didn't try to get anywhere. They were simply circling the block, probably looking for parking. More detailed studies in Los Angeles, in just one small business district, have estimated that within 1 year, the vehicles there in the search of parking have driven an additional 950,000 miles just to look for parking. And that, of course, wasted 47,000 gallons of gasoline, 732 tons of CO2 emissions. And these days, we're thinking about reducing our emissions. Wouldn't that be a great starting point? No lifestyle restrictions for any of us if we just could eliminate a lot of these waste due to the search for parking. So, next slide. What if we could come up with a system that provides us real-time or near real-time parking availability statistics? Similar to how we have real-time traffic on our GPS navigation systems today, imagine if your navigation system could guide you to areas where you're more likely to find parking. Also, we could feed that data to municipalities. Rather than doing one manual traffic survey approximately every 10 years and then using that to manage our parking infrastructure, what if we had detailed near real-time statistics of parking availability around our cities? Even small changes like changing prices on parking meters or changing the maximum stays that are allowed, installing additional parking meters in some areas can have dramatic effects on overall parking availability and these additional miles driven in the search of parking. Or how about if your, say, map that you're using for driving directions online would not only tell you that it takes you 45 minutes to get to Manhattan, but also tell you that at that time of day, you can expect an additional half hour cruising around for parking, or have the choice of paying $45 for a parking garage in that location. So how do we get all that data? Our idea is to use a fleet of mobile sensors, a fleet of cars that scan curbside parking slots as they drive by. And over here, you now see a map of the data plotted And the cars are driving right now. So if you're lucky, and if you watch that a little bit, we'll see some real-time updates coming in over the WIMAX infrastructure on that map. Now these cars use ultrasonic rangefinder sensors to detect the next obstacle at the side of the cars. Right? So as they're driving down this road, an obstacle likely is a parked car. If there's no obstacle or the obstacle is far away, that often is a free parking spot, as you're seeing down here. Over here, you see the setup of our prototype. We have the rangefinder sensors mounted here. There's an additional camera that we just use for research validation purposes, getting ground truth information. And then you see a GPS sensor mounted on top. So these rangefinder data is combined with GPS, sent through servers in the cloud, and then processed into these maps and into parking information. Now these sensors, in our experiment, we are attaching them to cars. And some modern vehicles do already have similar sensors built in, and there's potential for even reusing them. But overall, compared to installing sensors in the infrastructure, such as some cities are doing right now, putting them in parking meters for every slot, embedding them into the asphalt to detect parking availability, this is a mobile solution. One sensor can scan many parking spots as they drive by. So overall, it's a much more cost-effective solution. Let me actually say a few more words about the data you're seeing here. This is the raw rangefinder data. Green dots on this map represent long distance readings. Basically no obstacle detected at the side of the car. Red dots represent an obstacle detected, and that is often a parked car there. Right? Now, what is the challenge in this research? A large part of the challenges relate to mining this raw sensor data and extracting the actual parking spot availability in a city. Of course, not every free place that we detect at the side of a car is actually a legal parking spot. It might simply be a driveway. And our algorithms have to be able to learn the positions of legal parking spots over time and to give you an accurate estimate of parking availability. Not every obstacle that we detect at the side of the road is necessarily a parked car. Here's a planter that we detected during one of our experiments. And this is a time series trace of the ultrasonic rangefinder. If the algorithms are not carefully designed, the signature can look quite similar to that of a parked car that you're seeing further on the left. There are also challenges in accurate positioning. If you look here on the map, you see that in this area up there, the positioning errors are actually quite large. And that also happens to correlate with the high-rise buildings in the Brooklyn downtown area, the typical urban canyon effect, multipath, that affects positioning accuracy. In other areas, if we zoom out a little bit, you see the smaller buildings down here affect positioning accuracy less. Another challenge that our algorithms have to deal with. And addressing all these challenges requires large real-world data sets to validate and design our algorithms. So today we are conducting an experiment to collect such a data set. And you see we have 6 Parknet-equipped vehicles in Brooklyn that are driving into the coverage from the WIMAX base station and then transmitting their data. Over here, you have my colleague Thanasis, who is orchestrating, thankfully, the experiment over there in Brooklyn. In the background, you see a couple of cars. Cars are constantly coming and going.
Shall I speak? Okay. Hello, guys. Can you hear me?
Yes.
Okay. We are in Brooklyn downtown, and since this morning we are driving around Brooklyn, and the cars stream lively their data through our WIMAX base station to Rutgers, to the Parknet server at Rutgers, and they'll lively collect information about parking spots in Brooklyn. Actually, this is funny. Several people stop and ask us how they can get access to the application and see live parking information in downtown Brooklyn. This is kind of hard to get a parking spot here. So as you see, we have 8 cars participating in the experiment. And right now, a couple of cars will go out. Cars come and go. And as they drive around, they get the information about the parking lots and spots, and they are streaming them through WIMAX.
You see one car leaving there on the very right as we speak. Right? And you might see another couple of cars coming back home or leaving as we leave this connection on. Thank you, Thanasis. These cars have been driving actually for the better part of this morning already, taking various loops from the WIMAX cell, the staging area at Brooklyn Poly, and driving down certain roads and coming back into coverage. This sort of represents the area of coverage, and then cars are leaving on different areas. Here, we are sort of replaying information from this morning, and you can see a little bit the different routes that these cars have been taking on this map. And thankfully, so far, they've all followed their assigned routes. When we did the dry run last Monday, one of our drivers didn't take the exit just before the Brooklyn Bridge and ended up in Manhattan. Doesn't seem to be the case yet. All right, let me say a few words of how Genie actually helped us do these experiments and conduct this research. Here are the resources that we have used from Genie. Mobile clients. It was initially getting started. It was very helpful that we had already nodes that were equipped to get into a car. Saved us a lot of time. Right? WIMAX base station, we have one at Rutgers that we used extensively for testing. We are using the one at Brooklyn Poly because their parking situation there is obviously much more interesting than in our more suburban setting. We're also using the Genie backbone network to feed that information back to servers that are located at Rutgers University, so technically a different Genie aggregate. And in addition to this user application view that you have been seeing on this side over here, there's a set of software tools that we use to conduct this research. If we can bring up on this screen the visualizations provided by the OML measurement library that we're using to collect data. These are not custom designed for this particular application. It's just standard tools. As soon as you use this library, you will have available these plots. You can zoom into certain ranges of data. You can analyze the data, debug, just making your life a lot easier rather than having to write your own code. But what's so interesting about being able to plot some data, there's a lot more to these tools. OML, in particular, allows you to collect data from a distributed set of resources, and also from a potentially disconnected resources. So on each vehicle, for this experiment, we developed a set of sensor logging applications that feed their data into a local OML library. And this OML library then automatically connects through the Genie backbone to the data collection server located at Rutgers. It also does so gracefully if the cars become disconnected and later reconnect to the network. And in addition to this data collection and the automatic visualization that you get there, one can also use the OMF tools to orchestrate these experiments, to script these experiments. Right? Again, a distributed set of resources. There's the cars to control, there's the WIMAX base station to control, there are the application servers to start up. One can do from a single experiment script, and you see some examples of the scripts cycling through on the other side occasionally. this script through the control network will then start up all these resources. There are tools to take action at when the cars cross particular GPS locations that have been very helpful to optimize our data collection process, and so on. So in summary, I hope I'm convincing you that Genie is also useful for this kind of wireless application research project. And in particular for us, it has allowed us to cost-effectively experiment with a 4G WIMAX setup. It has allowed us to develop and harden protocols that deal with disconnected data or delay-tolerant data collection. It has provided us just existing hardware resources that were already tested, battle-hardened, speeding up our development cycles. It has provided us these tools for measurement collection in this highly distributed environment for orchestrating experiments, scripting experiments. And the feedback so far has been great. We've received the Mobisys Best Paper Award. We've received coverage, MIT Technology Review, and international Canadian press, and so on. And we look forward to scaling up this research and hopefully bring tools that show you available parking spots and available statistics soon. Thank you.